Hey everybody, welcome to I guess part 3 of the first year of Oregon Number Theory Days, and thank you for coming. Before I introduce our speaker, I just want to say that stay tuned after the talk. I'm going to tell you all about the exciting forms you get to fill out to be reimbursed for lunch, so that's going to come. It's my pleasure to introduce Dr. Rachel Pries, who I'm going to tell you a little bit about her. She got her PhD at University of Pennsylvania and then did a postdoc at Columbia before becoming a professor at Colorado State. She's a fellow of the American Mathematical Society and on the steering committee for Women in Numbers. She's been supported by the NSA and the NSF, and she's published over 40 papers. And I'm excited to hear what she has to say today.
Thanks, Derek. So I'd really like to thank all the organizers, all of whom I know, Shabnam, Derek, Clay, and Holly. And I'm really happy to come to Oregon. I actually don't know Portland very well. And I was coming in last night in the taxi cab. My taxi cab driver asked me why I was coming. And I said, well, I was coming for a math conference. He said, oh, I used to love math. But then I took this course in number theory. I said, oh, I'm so sorry. This is a conference in number theory. And I asked him what he didn't like. And he said that the very first homework, his professor assigned a problem, and he stayed up till 5 a.m. to solve this problem. Couldn't do it. And then the professor told him that it had taken people 70 years to solve that problem. And he felt hoodwinked that he had lost this night of his life and dropped the class and never looked back. And so I have to tell you that today I'm going to tell you some problems that are unsolved or which took over 70 years to solve. And even if we don't solve them today, we can still have rich and fulfilling lives and enjoy our day here today. Okay, so this is the abstract. So what I'm going to talk to you about today is that we're going to start with elliptic curves. And these are elliptic curves defined over finite fields. So they can be ordinary or supersingular. And then it turns out that distinction between being ordinary and supersingular, you can talk about that for curves of higher genus too. And so we'll talk about those finer invariants called the Newton polygon and the Dieudonne module. And this was a project that started at the Women in Number Theories 4. And what we looked at was to look at cyclic covers of the projective line. So those are sort of a generalization of hyperelliptic curves. And we tried to figure out which Newton polygons showed up for those kinds of curves. One thing that was really nice for me about this collaboration is that I'm really somebody that's studied curves a lot. So that part of the theory is very familiar to me. But some of my collaborators were people who studied Shimura varieties more. And so it turned out that putting those two pieces together, we were able to find these Newton polygons for these cyclic covers, which hadn't been found before. And as an application, we give new examples of supersingular curves of genus 5 through 11. And so my collaborators are Wanlin Li, Elena Mantovan, and Yunqing Tang. Not quite sure which way moves forward. There. Okay, so we're going to start with an elliptic curve over a finite field FQ. And here Q is a power of a prime P. And so it turns out, we'll see some examples in a minute, that the number of points on this elliptic curve defined over this finite field is approximately Q plus 1. And the error, which we'll call negative A, is a really important invariant for this elliptic curve over this finite field. So there's something called the Zeta Function of this elliptic curve over this finite field. And it's a rational function whose denominator is 1 minus t times 1 minus qt. And its numerator, 1 minus at plus qt squared, is a polynomial of degree 2 and has integer coefficients. And it just depends on a. And for those of you who have seen zeta functions before, one thing that this means is that the number of points on E over any larger extension of FQ is completely determined by this one number A. So what does it mean to be supersingular? Well, we can look at the coefficients of this polynomial. This one is a coefficient 1. It's not divisible by p at all. And so we're going to put this point right here at 0, 0 to keep track of the fact that this coefficient is not divisible by p. Now this coefficient is divisible by p a whole bunch of times, but once we normalize it, we can see that somehow it's just divisible by q once. And so we're going to keep track of that by putting this point here at coefficient 2 is divisible by q once. And so we draw this point here. So the real question comes down to whether the number p divides a or not. So if the number p does not divide a, then its p-adic valuation is 0, and so we put this point in here. But if p does divide a, somehow this point is up here. And when we draw the lower convex hull, we get two different pictures here for what is the Newton polygon of this polynomial. And this is the case that happens almost all the time. And this is called being ordinary. We say that the slopes of this polynomial are 0 and 1. And this case happens rarely, but it does happen. In this case, the lower convex hull of these 3 points has slope 1/2, and we call that being supersingular. And so this is the big difference between the zeta function of an ordinary or a supersingular elliptic curve. So, okay, so there are lots of facts that are known about supersingular elliptic curves. First of all, for every prime p, there exists one of them. In fact, all of them are going to be defined over fp squared. And the number of them, there's an exact formula for it, and it's approximately p over 12. Another way of thinking about a supersingular elliptic curve is that the endomorphisms of E should be a non-commutative. It turns out they'll be in order in a quaternion algebra. And here's some examples of supersingular elliptic curves. So if P is 3 mod 4, we can look at y squared equals x cubed minus x. And remember that this is an elliptic curve with complex multiplication because you can send x to negative x and y to iy, and that gives you an automorphism of order 4. And it turns out the endomorphism ring of E contains z adjoint I, and for P being 3 mod 4, this prime is inert in z adjoint I, and that's what's used to show that this endomorphism ring of E is non-commutative. In fact, this automorphism of order 4 does not commute with the Frobenius. Another example is when P is 2 mod 3, then this is a similar example. Y squared equals x cubed plus 1 also has complex multiplication. So there's some other ways of thinking about an elliptic curve being supersingular. So it turns out, so this is elliptic curve is a group, and we could look at the points that are p torsion points. So those are the points that have order dividing p. And it turns out being supersingular is equivalent to having no points of order p, not just over the field fq, but over any extension of fq. So this says that the number of p torsion points over the algebraic closure fp bar is just the identity. And there's some other ways of describing this. One way is that there's a Cartier operator that acts on the one forms, and you can see whether or not that Cartier operator annihilates the one forms. The one forms are just dx over y. And so Augusto looked into that and figured out if you write your elliptic curve as y squared is a cubic, h of x, where h of x is a cubic with distinct roots, you can figure out whether or not it's supersingular by looking at the coefficient of x to the p minus 1 in the p minus 1 over 2th power of h of x. And that's what ends up getting used in order to show that there are approximately p over 12 elliptic curves that are supersingular for each prime p. So feel free to stop me at any point if you have questions. Okay, so more generally, we could look at a curve over a finite field that has higher genus. So for instance, it could be a hyperelliptic curve, y squared, it's a polynomial of higher degree, or it could just be an arbitrary curve. And there are the Weil conjectures, which say that you have a zeta function of this curve. And again, it's going to be a rational function with denominator 1 minus t, 1 minus qt, and the numerator is the L polynomial. And again, this is a polynomial that has integer coefficients and has degree 2g. And so that polynomial, we could factor it over the complex numbers. And it's going to look something like this. And the Weil conjectures say that the absolute value of the reciprocal roots is square root of q. So this polynomial tells you about the Frobenius endomorphism on the Jacobian. And these numbers, alpha I, they're called the Weil numbers of the curve. And these numbers, again, determine the number of points on the curve over every extension of FQ. So, okay, I probably put too much on this slide here, but the idea is that, again, we could look at this polynomial and look at its coefficients and measure how much they're divisible by p. And that's called the Newton polygon. And what it keeps track of is it keeps track of the p-adic valuations of these numbers alpha I. And so we're going to draw this, this lower convex hole of these points, and it has some things in common with the elliptic curve case. So again, this is going to be a polynomial that starts at 0, 0. It's going to end at the point 2g, g. And so it's sort of a polynomial that kind of looks like this. And one thing that's known about these polynomials is that it's made up of line segments that break at points with integer coefficients. And if any slope, like the slope 0, occurs with a certain multiplicity, then the slope 1 is going to occur with the same multiplicity. And so if the slope 1/3 occurs with a certain multiplicity, the slope 2/3 has to occur with the same multiplicity. So there's a sort of a symmetry on these Newton polygons. One thing that's, this length of this part is going to be important for us a little bit later. Let's call that length f, and this number f is called the p-rank of the curve. But what it means to be supersingular is that you don't have any slopes except for the slope of 1/2. So being supersingular means that this curve, its Newton polygon, should be just one line segment of slope 1/2. And that seems like kind of a random property, but it turns out that it can be written in so many different ways. And that is one indication that this property is sort of canonical or important for curves over finite fields. So, okay, so we've already said what it means to be supersingular is the Newton polygon is a line segment of slope 1/2. It turns out that that property, it tells you something really important about these Weil numbers, alpha I. So, oh, sorry. How do I fix that? Let's see.
I didn't even know that was possible.
Oh, yeah, yes. Any questions in the meantime? Oh, thanks. There. Okay, so these numbers alpha I, remember that they had absolute value root q. So they're on a circle in the complex plane that has radius root q. So when we normalize them, they're going to be zeta times root q for some zeta on the unit circle. It turns out being supersingular is equivalent to those numbers being roots of unity. So, you know, in general, these numbers could be anywhere on the unit circle, but being supersingular means that some power of them should be 1. And that turns out to be equivalent to this curve being minimal. So remember that for a curve over a finite field, the number of points is bounded by the Hasse-Weil bound between a lower bound and an upper bound. And all the time people study the ones that are maximal, that have as many points as possible. But you could also study the ones that are minimal, that have as few points as possible. So it turns out that being supersingular is equivalent to the curve being minimal over some extension of the finite field. So some of those curves will be maximal as well over a smaller extension of the finite field. So, so if you're interested in maximal curves, curves that have as many points as possible over a finite field, those are all going to be supersingular curves. So Tate proved that this was equivalent to the endomorphism ring of the Jacobian being a matrix algebra over the quaternion algebra ramified at p and infinity. And Oort proved that for a supersingular curve, the Jacobian breaks up completely. It turns out that it's isogenous to a product of supersingular elliptic curves. So those are all equivalent formulations of what it means for the curve to be supersingular. So, and so here's an open question. I don't think it's 70 years old, but an open question about supersingular curves. Maybe it's 40 years old. Is, let's say you pick a characteristic, the prime p, and let's say you pick a natural number g, which will be the genus of the curve. And does there exist a supersingular curve of that genus defined over a finite field of characteristic p? So in this question, we give up on trying to figure out the field of definition of that curve. So whether it's defined over fp or fp squared, that we don't care about. We just want it to be defined over some field of characteristic p. And so here's what's known about this question. So the answer turns out to be yes for elliptic curves. That's the result of Düring. For curves of genus 2 and for curves of genus 3. For genus 3, that was probably proved in maybe the 90s. It turns out also from the 90s, the answer is yes for the characteristic 2. And van der Heer and van der Vloot, they ended up constructing supersingular elliptic curves in characteristic 2, in fact, defined over the field F2, smallest finite field, for all genuses G. And one thing that's very nice about their construction is it's completely explicit. If you pick your genus, their algorithm will give you the equation for this supersingular curve. So, so if you generalize their construction to an odd characteristic, you still get supersingular curves, and you can get the genus to be arbitrarily large. But you don't hit every genus. You hit sort of an arithmetic progression of the genuses for a fixed odd prime p. So Faber and van der Heer proved something weaker than supersingular. They proved that for all primes p and for all natural numbers g, you could at least get a smooth curve of genus G with p rank 0. And I forgot to define the p rank, but it's this number here. So saying that you have p rank 0 means that you have no slopes of 0 in your Newton polygon. And that having p rank 0 is equivalent to having no p torsion points over the algebraic closure of fp. So this is kind of promising because it says that at least we can produce a smooth curve of genus G with p rank 0. And those would be, in fact, there are quite a lot of them. And so those are candidates for curves that could be supersingular. But one drawback of this stuff of Faber and van der Heer is it's completely non-constructive. So they have no way of actually finding the equation of one of these curves. And in fact, something I proved with Jeff Actor is that most of them won't be supersingular. So most of them are going to have slopes like 1 over g, g minus 1 over g. So, so for those of you who like to think more about geometry, you can rephrase this question completely in terms of geometry. You have the moduli space of Abelian varieties of dimension g. And inside it sits the Torelli locus, which is the moduli space of Jacobians. But it's a very high codimension. And the supersingular locus inside of AG also has very high codimension. So one way of phrasing this question in a geometric way is that within the moduli space of Abelian varieties, here we have two canonically defined subvarieties that have very high codimension. Are they going to intersect or not? And that's another way of thinking about this question. The last time I gave this talk, at the end, somebody said, like, you should have told us what you think about this question. Is the answer going to be yes or no? And I don't know, if I really had to put a money on it today, I think I would say that the answer is no, that there should be genuses and primes p for which there does not exist a supersingular curve in that characteristic. But how would you go about finding that they don't occur is just as hard as showing that they do occur. Okay, so let's look at cyclic covers of the projective line. So you're going to pick a number m, bigger than or equal to 2. And we want to look at equations that look like y to the m is a product of x minus some value to the ai. So these are a generalization of hyperelliptic curves, which is the case where m equals 2. And so what we're going to do, so we're going to ignore, if you just multiply this out, you get then a polynomial of some high degree depending on these values ai and the number of b's. And we're going to keep track of these a's. These are integers that are between 0 and between 1 and m minus 1. So and those a's are called the inertia type. So if you're familiar with the hyperelliptic case, the a's are all 1, and that's the only option for them. So, but once you get up to m, for instance, m equals 3, we could have the a's can be either 1 or 2, and you can sort of look at any combinations of 1s and 2s that you want. So one way of thinking about this is that here we have a variable y and a variable x. And so if we think about the variable of x being a coordinate on the projective line, then we have a cover, and this is a z mod m cover. The automorphism of order m, what it does is it takes y and sends it to an mth root of unity times y. So we have a z mod m cover of the projective line, and the places it has problems are at the points bi. So those are the branch points of this cover. They're the points where you have only fewer options of what y should equal rather than m. So we have this cover, it's branched at these points. And let's think about what these numbers ai are representing. So we could think about the plane, the projective line, and take away these points and look at the fundamental group on that. And that's a free group. It's generated by these loops that go around the missing points. And then there's a relation where the product of all those loops should be 1. And so from topology, we see that there's a bijection between covers like this and maps between the fundamental group and z mod m. And this cover corresponds to the map which takes the loop li to the value ai. And so what that means is that because these loops have this relation that the product of the loops should be 1, it means that the a's should have a relation too, that the sum of the a's should be 0 mod m. It also turns out that this curve is connected if and only if the GCD of all the a's with m is 1. So those are the restrictions that we're going to take on the inertia type. So sometimes we worry. So another way of thinking about this is that, for a hyperelliptic curve, there's always the case, do you have a hyperelliptic curve being an y squared being an even degree polynomial in x or an odd degree polynomial in x? And that condition, whether this polynomial has even or odd degree, determines whether it's what's happening at infinity, whether the cover is branched at infinity or not. And so this is sort of a similar situation here where the a's, since they all have to be 0, when you add them up mod m, if somebody handed you an equation like y to the m is something like this, you could tell whether or not it's branched at infinity by whether the a's you're given are adding up to 0 mod m. So the a's tell you something else as well. So if a1 is relatively prime to m, it tells you that that there's exactly 1 point over the point x equals b. And if the GCD of a with m is not 1, it tells you that there are several points over when x equals b. So you can figure out how many points there are over these ramified points. And from that, you can look at the Riemann-Hurwitz formula, which tells you the genus of y. And so the Riemann-Hurwitz formula usually says 2g minus 2. So there's the 2g, there's the minus 2. Is going to be a multiple of m times So this has been rearranged a bit, but this is the contribution. These points contribute to the genus of the formula. Okay, any questions about this? Okay, so we've got these Z mod M covers. And so what's nice about these Z mod M covers is that the Jacobian carries an action by Z adjoined mu M. So there's an action of order M on every group associated with this curve, and in particular on the Jacobian. And once you have an action like this, you can divide up any vector space that carries an action by this into eigenspaces, where certain things have, when you act by the mth root of unity, they change by multiplication by zeta m. Some of them change by multiplication by zeta m squared. So any kind of vector space that carries an action like this, we can divide it up into eigenspaces. And it turns out that we can figure out how big these eigenspaces are, and those dimensions depend only on these numbers a. So since our base curve is the projective line, the trivial eigenspace is going to vanish. And so for all the other eigenspaces between, as n ranges from 1 to m minus 1, you get an eigenspace, and there's a formula, it goes back to work of Connie, for what these dimensions of these eigenspaces are. Okay, so let's just look at a really concrete example here. Let's take m to be 7. Let's take 4 branch points. And let's say the inertia type is 2, 4, 4, 4. So here's an example of a curve that would have that type. Y to the 7th is x squared, that's the 2, x minus 1 to the 4th, x minus t to the 4th. Here t is just some number, for instance, the number 2. And then the extra 4, I've pushed that out to infinity. So we don't have to view it in the equation. Or you could take x minus 3 to the 4th as well. So it turns out that when you do the Riemann-Hertz formula to this example, the genus turns out to be 6. And these are the dimensions of the eigenspaces. So the first one has dimension 1, and then 2, 0, 2, 0, 1. You can see how there's a complex conjugation acts on everything in sight. And in particular, it takes one eigenspace to the opposite eigenspace. So in this case, the first eigenspace is somehow connected to the 6th one, and the second to the 5th one. And notice how the sum of the dimensions always adds up to 2 in this example. So far, everything we've said here could be said over any field other than F7. And so where are we going to get a prime? The way we're going to get a prime is by reducing this equation mod p. And so we have to pick a prime p, and you could pick any prime that you want. But the congruence value of p mod m, or in this case p mod 7, is then things are going to be really different depending on the congruence of p mod 7. And the reason for that is that there's a Frobenius action also, and it permutes these eigenspaces as well. And the way it permutes these eigenspaces is it takes ln to lpn. And so depending on what p is mod m will really change the orbits of this action. So for instance, if p is 1 mod 7, then these eigenspaces will each be in its own orbit under the Frobenius. Whereas if p is 3 or 5 mod 7, then they'll all be in the same orbit. So somehow all this stuff about the genus and the inertia type and the signature type, that doesn't depend on the prime at all. But when you reduce mod p, then suddenly the value of p mod m plays a big role.
Rachel?
Yeah. Yeah.
When you're thinking of this action on the Jacobian, are you really thinking of it as action on the one forms?
Yeah, or H1 of O. Yeah, these dimensions are for H1 of O, but you could also think about it on H0 omega 1 on the one forms. Yeah. Yeah, that was a great question, by the way. Any other questions? So,
I do have one more question on
Yeah.
the L-N
yeah,
on the last slide.
yeah.
The N are coming from 1 to N minus 1.
Yeah. Yeah, and
So I don't understand where the index N comes from.
yeah. So the to start off with, the index would be from 0 to m minus 1, corresponding to an action by zeta m to the n. But
And zeta m is the primitive m through the community.
right,
I see.
right. But the when n equals 0, that's the trivial eigenspace, and that corresponds to the Jacobian of P1, and that disappears. Yeah, yeah, that was a great question. Let's see, any other questions? So Irena Bau used this Frobenius action on the eigenspaces. And her goal was to figure out an upper bound for this number f, the p rank of the curve. And the way that she did it was to think about the this number f turns out to be the stable rank of the Frobenius. And so the stable rank of the Frobenius is sort of bounded by its rank at any, like let's say you have to take g copies of the Frobenius, the stable rank is somehow going to be bounded by its limiting factor. So another way, let me say that more clearly. So the Frobenius moves these eigenspaces around. And some of them are bigger and some of them are smaller. So if you want to find the rank of the Frobenius, you get no condition when you look at it on acting on a big eigenspace. But then if it has to act on a small eigenspace, then its rank is going to be small because it's bounded by the dimension of that eigenspace. And so what she did was to think about within each orbit of Frobenius on these eigenspaces, what's the smallest dimension of the eigenspace? And that's going to put a chokehold on the rank of the Frobenius operator. And so to say that more in terms of a formula, let's look at the dimension of these eigenspaces as you go in an orbit under the Frobenius, and take the smallest dimension of that and then multiply it by the number of things in the orbit. And if you add that up for all the orbits, that should put an upper bound on the rank of the Frobenius operator. And under mild conditions, she showed that this upper bound is realized. Okay, so let's look at an example. So this case where m is 7, and we were looking at this case where this is the signature. So if p is 1 mod 7, then each eigenspace is in its own orbit. So there's no condition at all coming from this situation. And to find the upper bound, you just add up the dimensions of the eigenspace, and that's going to be 6, which is the genus. So if p is 1 mod 7, this upper bound is just the genus of the curve. There's no condition. If p is 6 mod 7, the Frobenius then identifies these opposite eigenspaces, and they each have, and so this one, if you look at and on these two, there's a 0 showing up. So the upper bound for the p rank on these two eigenspaces orbits is going to be 0. So the only place you could get a non-trivial rank of the Frobenius is from this orbit, and so that gives you a bound of 2. And so on. So let's, for instance, look at this case where p is 3 and 5 mod 7. Then the orbit of Frobenius is all of the eigenspaces. And so the upper bound for the rank of the Frobenius is bounded by the sort of the smallest bottleneck, which is this 0. And so this upper bound is 0. And so what this says is that, let's say you wanted to look for supersingular curves. The best option, if you're looking at curves that look like y to the 7th is something like this, is to look at cases where p is 3 and 5 mod 7. Because those curves are all forced to have p rank 0, which means that they don't have any slopes of 0 in their Newton polygon. So if you want to find supersingular curves, looking at these curves where p is 1 mod 7, you're not going to have much luck, because most of those are all going to be ordinary. They're all going to have, most of those are all going to have slopes only of 0 and 1. But if you look at P being 3 or 5 mod 7, then at least all of those have P rank 0. And so there's a much greater chance that those are going to be supersingular. So the question now is, okay, this tells us about the P ranks of these curves, but what are the Newton polygons, and when are they supersingular? And in general, finding these Newton polygons of curves, they're not easy to compute. And so we wanted to find a more geometric way of doing that. Okay, so this is our first result. So we looked at the case of 3 branch points and found that there exists a smooth supersingular curve of genus G over FP bar in all these cases. So from G is 4 to 11 under these congruence conditions on P, and so on. And so the case that we were just looking at is this one here, P being 3 or 5 mod 7, and the genus 6 curves. That's going to produce part of this line of this table. So okay, so this result is very long. It fills up a whole slide, but it's somehow unsatisfying for a couple different reasons. The first one is that somehow this was already known. It comes out of the case because for a 3-point cyclic cover of P1, the Jacobian has CM, and there's something called the Shimura-Taniyama method that allows you to compute the Newton polygon. So this is sort of the proof of this is very straightforward, knowing well-known things in the literature. Somehow just nobody had ever written down before when you get a supersingular curve using that method. So this is not a big result, but nobody had written it down before. The thing for me that's a little unsatisfying is that it would be so nice to be able to say for genus 7 there's a supersingular curve for all P. And that's just not what this method produces. Because of this Frobenius action on the eigenspace, there's always going to be a congruence condition coming in these results. One thing that's nice about it, though, is that once you get up to these higher values of G, in particular G being greater than or equal to 9, those are situations where, for a geometric reason, you would not expect there to be a supersingular curve of that genus. Because within the moduli space of abelian varieties, the Torelli locus of Jacobians has such high codimension, and the supersingular locus has such high codimension that you would not expect them to intersect. And so these are maybe some of the first examples of sort of these unlikely intersections that come from something really different from the van der Heer and van der Vloot construction. Okay, so then we said, well, what if we go beyond complex multiplication? So what if we stop looking at the case with 3 branch points, where capital N is 3? What if we look at more than 3 branch points? And let's look at a family of Z mod M covers of the projective line. And so we're going to get a family of curves, and it has positive dimension because you get to choose the location of the branch points, and there are lots of branch points now, so you have lots of choices. And so the question is, which Newton polygons appear for curves in that family? So it turns out that now the theory splits a little bit, because if you like abelian varieties and Shimura varieties, you would say this question is completely understood, because there's all this work of Weymann and Vedhorn, based on earlier work of Kottwitz, Wrapup, and Richards, which completely classifies which Newton polygons show up. But on the other hand, not every point among the Shimura variety comes from the Jacobian of a curve. So again, we have the locus of Jacobians being a subset of the abelian varieties. And so figuring out which of the Newton polygons that show up for the Shimura varieties show up for the Jacobian of a curves, that gives us the same sort of issue. So most of the time, these abelian varieties are not Jacobians, but there are a few cases where we might be lucky. And in those lucky cases, almost all of the abelian varieties that carry an action of mu-m come from Jacobians of curves. And it turns out that Moonen completely classified when that's going to happen. So he found that there were 20 special cases. And what does it mean to be a special case? It means he found what M is what M, the degree of the cover, and N, the number of branch points, and what the inertia type A is, and then you can figure out what the signature type is. And he found that there were exactly 20 cases where the dimension of the family of curves, which is the number of branch points minus 3, because you can move 3 of the branch points to 0, 1, and infinity, equals the dimension of the PEL Shimura variety. So if you look at Moonen's paper, there's this table with 20 lines in it. And so what we did was to look at that table and say, well, here's a place where we could actually figure out which Newton polygons occur for Jacobians of curves, because we know what's happening with the Shimura variety, and almost all the points on that Shimura variety are the Jacobian of a curve. Okay, so what comes out of that then? Yeah.
So could you quickly remind us what a Shimura variety is?
Yeah, I'm not an expert on Shimura varieties, but here's the way I think about them. So you want to have an abelian variety, but you want it also you want to look at abelian varieties, but you also want them to carry an action of mu m. And then once you say that you want to have that action of mu m, you also need to classify the signature type of that action. And then you want to look at all the abelian varieties that have that structure. And that makes a subset of the moduli space of abelian varieties. And then you put some level structure on it, and then you get some kind of geometric object that classifies those objects. So it's a moduli space for these abelian varieties with this extra mu m action. Yeah. But there are a lot of technicalities that I was not in charge of. So, okay, so anyway, so this slide is maybe the most technical here, that if you have this action of mu m on an abelian variety, it's going to put constraints on your Newton polygon. And these are similar to the constraints of Bell on the P rank. So again, the Newton polygon is going to split up into pieces. The Dieudonne module, which is sufficient to determine the Newton polygon, is going to split up into pieces, and those pieces are going to be indexed by the orbits of Frobenius on the eigenspaces. It turns out that the multiplicities of the slopes have to be divisible by the number of things in the orbit, and that's because there's an action of the residue field on each piece. There's also a Rosati involution, and so that tells you a symmetry condition that the slopes, once a slope occurs with a certain multiplicity, then the slope 1 minus it occurs with the same multiplicity. And then there's actually a formula, and I guess this is probably due to Kottwitz, for what the most typical Newton polygon is going to be in that family. So here's an example. Let's look at M being 7, and this inertia type that we were looking at before. And this was the signature. And so let's say P is 3 or 5 mod 7. So the Frobenius acts transitively on these eigenspaces. And Bau's result says that this has P rank 0. So all the slopes have to be positive. And it turns out that because 3 and 5 have order 6 mod 7, that tells you that the multiplicities of the slopes have to be divisible by 6. And so at that point, there are only 2 options left. You could either have slopes 1/3 and 2/3, each showing up with multiplicity 6, or you could be supersingular with all slopes being 1/2. So those are the only 2 options, and both of them, from the perspective of which Newton polygons occur, are very interesting because they're pretty unusual Newton polygons. So this is going to be maybe one of the most interesting cases to look at, because whether you get something that looks like this or something that looks like that, neither of those were known to occur before for the Jacobian of a curve. So what we did is we took the table and we computed all the Newton polygons for all the entries of the table. And most of them were kind of boring. But there were a few cases that we got things that had not been shown to occur before. So in particular, when the genus is 5, 6, or 7, And so here's this case when the genus is 6 and P is 3 or 5 mod 7, you get something that's supersingular. And so that shows, with a little more work, that's going to show that there exists a smooth supersingular curve of genus G over this field of characteristic P in these cases. I know there are a lot of people in the audience who like modular forms and things like that. So let me just mention this one remark that the last time I talked about this result, John Voigt and Ling Long pointed out that that there might be a different way of doing this whole theorem without using PEL Shimura varieties, but instead using truncated hypergeometric functions. And the idea there would be to look at this family of curves, which is a one-dimensional family of curves, and look at these hypergeometric functions and show that you have these special values for those functions and that you have sufficiently many special values, and those special values are where it's going to be supersingular. I don't know if that made any sense there or not, but so when they first told me that, I was like, oh no, our whole result is like going to be like subsumed by hypergeometric functions. But I don't think it is. First of all, because like it seems like that stuff isn't really fully written down. So they got kind of interested, but it doesn't seem like it's currently in the literature, any of this stuff about the hypergeometric functions. And beyond that, it seems like what this would tell you is that one of the unusual Newton polygons occurs, but it doesn't tell you which Newton polygon it would be. And so to actually figure out which Newton polygon would show up, I think you'd have to go back to the Shimura varieties and sort of figure out what are the options for the Shimura varieties in that case. And if you weren't on a special family, then you would also have additional things to worry about. So I think that would be a really interesting thing to pursue, but it doesn't really affect this result. And then we also looked not just at the supersingular Newton polygon, but other ones that were unusual but not supersingular, and we found that 20 new things occurred under congruence conditions on P, and also 11 new Ekedahl-Oort types occurred. I think in the interest of time, I'm going to skip the Ekedahl-Oort type, but I'd be happy to talk about that a little bit later. The idea there is you have an action of Frobenius and Verschiebung and it tells you about the isomorphism class of the p-torsion group scheme. So I've already talked about the computation, which is to compute all the Newton polygons for Munin's families. But there is one more theoretical issue, is that you have to think, do they occur for a smooth curve in the family? The problem is that you can have singular curves. So you could have a singular curve that looks something like this, where these intersect in an ordinary double point. And this is sometimes drawn like this to show that we have two curves intersecting in an ordinary double point. And so this curve is singular, but when you look at its Jacobian, the Jacobian of x breaks up as the Jacobian of these two pieces. And this is a perfectly valid Abelian variety. There's no problem with that Abelian variety. So in the Shimura variety setting, we produce an Abelian variety, which is the Jacobian of a curve that has a particular kind of Newton polygon. But from the curve point of view, we would be unhappy if it came from the Jacobian of a singular curve that looked like this. And so there's a theoretical piece here to show that we want these Newton polygons to show up for the Jacobian of a smooth curve. And that's especially important because a lot of these Newton polygons are things that come apart in pieces. And so they would be very likely to occur for the Jacobian of a singular curve. In fact, it'd be easy to show that they show up for the Jacobian of a singular curve. So we want to say that they show up for the Jacobian of a smooth curve. So for the most typical Newton polygon in the family, this is no problem because it comes from one of the typical points of the covers of curves, and that one's automatically smooth. So for the ones that are the most ordinary one in each family, we get this for free. But a lot of the interesting Newton polygons that we produced came up from more unusual Newton polygons within the Shimura variety. So, and so we had two different strategies for showing that they came from the Jacobian of a smooth curve. One was to say that, okay, it is true that this abelian variety could split up, and it is true that this Newton polygon could split up, but it couldn't split up with the mu-m action. And so because everything carries a mu-m action, and these curves have a mu-m action, if this thing split up into two pieces, each piece would have a mu-m action, and some of them we can just exclude because if you split them up, they wouldn't have a mu-m action on the pieces. And so that is one strategy to show that they come from a smooth curve. The other strategy is more complicated, and it comes from looking at the basic Newton polygon. And what the Shimura people on the team did was to generalize theorems of Vollard and Volhard-Renner about the number of components of the basic locus going to infinity with P. And so, so one thing so here's one example that we didn't talk about through the talk, which is the case where the genus is 6 and P is 2 or 4 mod 7. It turns out you get interesting slopes in that case too. You get slopes 1/6 and 5/6. And one thing that's nice about slopes 1/6 and 5/6 is it's the most typical Newton polygon for something that has P rank 0. And so what we're currently working on now is using the things we've produced from the Shimura variety setting and doing an inductive result to show that you can produce things of arbitrarily high genus which have interesting Newton polygons. And so so the idea here is to find an interesting Newton polygon that shows up in some small genus, for instance, like the genus 6 ones we've been talking about, and to use geometric methods to produce things of higher genus that have interesting Newton polygons. And so along those lines, the most interesting thing that we've been able to find is that if you have a prime which is 2 mod 3, and if you pick any G, natural number, that there exists a smooth curve of that genus defined over FP bar, which is 2/3 ordinary and 1/3 supersingular. So in other words, we can't show that there are supersingular curves of every G, but we can show that there are curves that have lots of slopes of 1/2. So when you look at all of the slopes, you get a lot of slopes of 0. Then you get a lot of slopes. So here, this is G. So you get lots of slopes of 0. You get lots of slopes of 1/2, and then you get lots of slopes of 1. And so these curves are not supersingular, but they have the property that the multiplicity of the slope 1/2 part of their Newton polygon is very high. Okay, so and just in the last couple of minutes, I just want to put in an ad. So I love to travel. Actually, I'm not sure that's true after yesterday, but in general, I really love to travel. I love visiting new places. I love meeting people and talking about all the ideas, hearing what other people are doing mathematically in many different places. But as a result, my professional carbon footprint is really high. And I think anyone who wants to get into professional mathematics ends up traveling a lot, because that's a crucial part of our job. It's what makes mathematics vibrant. But in order to feel better about this, I want to tell you that I'm now a supporter of Climate Solutions, which is a Portland-based organization working on accelerating the transition to our clean energy future. I don't know if you've heard of them at all, but they seem like a really, really cool organization. And I also wanted to say that in the fall, CSU is going to be advertising 2 tenure-track jobs, and we'd like to have a very vibrant pool of applicants. One of the jobs is in number theory combinatorics, and one is in big data. So please spread the word about those things as well. Yeah. Thank you.
All right, any questions for Rachel? Any more questions?
More questions. So if M, the degree on Y is highly composite, one could imagine there would be lots of intermediate curves. Is that held? Is that?
Yes. So in Moonan's families, most of the degrees are prime, but there are a few that are not. So, so degree 9 and 12 covers, and so in that case, the Newton polygon definitely is going to break up. It's sort of hard to get both pieces to be simultaneously supersingular, but under certain, so I think in our supersingular result, 2 of those came from composite degrees. Yeah, you could also look for, Moonan's families are all cyclic covers of P1. You can also look for abelian covers of P1. Those haven't been completely classified, so there are more opportunities for those things to be special in that the moduli space of Jacobians is open and dense, and the moduli space of the Abelian varieties. So yeah, it's a really good question.
Any other questions?
Does the definition of supersingular generalize to Abelian varieties that might not be Jacobians of curves?
Yeah, and it's sort of, and so the slopes of the Frobenius make sense. That definition makes sense, and the Dieudonne, there's a Dieudonne module definition where you can just find the slopes of a p-divisible group, and so that the supersingular property totally makes sense on Abelian varieties. And actually, it's kind of better understood in that context because there are these results of Chai and Oort where you can, they have a Newton polygon stratification on the moduli space of Abelian varieties. And they know lots of things about that stratification, like the dimension of each strata and which strata are in the boundary of which others, and in particular, the supersingular locus. Most of the strata are irreducible, except for the supersingular locus. And the supersingular locus breaks up in a certain number of pieces, and they know the dimensions of those pieces, and they have they just really know a lot in that setting. But the piece that's really not known is how the moduli space of Jacobians sits inside that setting.
So how about the question of, does there always exist an Abelian variety of dimension G supersingular over FP?
That I don't think is known. Yeah, so well, you can find a super special one. So maybe that would be the way to go about that. Is instead of looking at being isogynous to a product of supersingular curves, you could just say, let me take something isomorphic to a product of supersingular elliptic curves, and you could get that defined over FP. Yeah, so that would be known. Those are kind of what Oort did, was to start with a product of supersingular elliptic curves, and then to factor out by isogenies of degree p, and he used that to show that he could somehow parameterize the supersingular locus inside the moduli space of Abelian varieties. So, yeah.
And is there a genus G generalization of the theorem of Elke's that there are always infinitely many supersingular primes associated to an elliptic curve over Q?
I don't think there. I don't believe that has been generalized. Actually, Jeff Actor has looked into some things similar to that, but the generalization is much more subtle. It's not as straightforward as you can reduce and get infinitely many primes, or it's supersingular. It's a much more complicated condition.
Any more questions? All right, let's thank Rachel.
Yeah.
All right, we have a 20-minute break before our next speaker.